Hi everyone, my name is Adriana Ladera, and today I want to talk to you about how we can explore transition metal complex space with computation and artificial neural networks. A transition metal complex, or a TMC, is basically just a molecular system with a transition metal in it, but this can also make studying the electronic structure of this system a little bit more complicated. However, it can also motivate improving the computational tools that are available to study the electronic structure of these systems. Now, of the computational tools we have, there's DFT, density functional theory, which is one of the most widely used methodologies for studying the electronic structure of molecular systems. This is because DFT is computationally efficient, so it's accurate without being too computationally costly. Now, under DFT, there are these things called functionals, which all vary in accuracy, meaning they all have different ways of describing the electronic structure of a system. Sometimes they have similarities across the functionals, or sometimes they can disagree, so they have very little similarity in terms of how each functional describes the same system. In the case of TMCs, however, DFT is actually prone to predictive performance inaccuracies. So what we're trying to do is we're trying to find TMCs in which functional disagreement is the largest. So in this example, that would be this complex right here. Because in the event that future scientists want to develop new electronic structure methods beyond just DFT, we can test the robustness of these methods with TMCs that have large functional disagreement, which would be an interesting property to test. So the way that we go about this is we have these sets of revised autocorrelations of our TMCs, or racks. So what a rack is basically just a connectivity of a molecule, which shows how the surrounding atoms are connected to the transition metal. And we have these as inputs to train our neural network. And another thing that we do is we also have, we apply to our TMCs a functional, and we use it to compute a certain property. And these properties will become our weights to help us initialize our neural network. And then what we expect is our neural network will predict how it thinks other functionals are going to compute the same property computed by our initial functional and our initial weights. I did mention earlier that we were looking for TMCs in which functional disagreement was the largest, and so we use this metric called alpha, which basically measures how much a functional disagrees with another function. So again, since we're looking for large functional disagreement, we're looking for a large value of alpha. So in this case, that would be this central TMC right here, because this has the most functional disagreement. We can actually visualize our results through use of what's called a UMAP, which stands for Uniform Manifold Approximation and Projection. So this is basically each of these points is representative of a TMC, and the colors actually do mean something. So I mentioned earlier that our neural network wants to predict a property, and that property is total atomization energy. The definition here isn't too relevant, it's just that we're using atomization energy to understand our UMAP. So in this case, warmer regions represent smaller absolute values of atomization energy, and cooler colors represent larger absolute values of atomization energy. Also, the point size is correlated to the value of alpha. So in this case, a larger point size would represent a larger value of alpha, meaning more functional disagreement. And just based on qualitative observation, we can see here from this UMAP is that regions that tend to have warmer colors have a higher ratio of larger points, meaning a higher value of alpha. So what we can infer from this UMAP is that complexes or TMCs that have a smaller absolute value of atomization energy tend to have more functional disagreement. Now this is a UMAP for B3lib, which is a mid-tier accuracy functional, but if we wanted to compare it with a low accuracy functional, we can see that although the shape of the UMAPs is slightly different, we notice that both functionals agree that smaller absolute values of atomization energy are more likely to have larger functional disagreement. So we can move on from here, and what we can do next is we can actually take those TMCs that have large functional disagreement, meaning large values of alpha. And based on our UMAP, what we saw was it was actually the TMCs that have smaller absolute values of atomization energy, which tend to have larger functional disagreement. We're going to take our neural network and have it learn this information so that way it can screen the entire transition metal complex space for these types of complexes that have large functional disagreement, which in that case it would be screening for complexes that have smaller absolute values of atomization energy. Lastly, I want to conclude this presentation by thanking my research advisors, so that would be Chenru and Vaishnavi. They're both PhD students here at MIT, and I really appreciate them being able to make sure that I understood everything to the best of my ability, so that way I could be successful in my project. I also want to thank Dr. Kulik for taking me under her wing, and she's also the principal investigator of the HJK group. So I want to thank them for being super welcoming to me throughout the entire summer. And lastly, I also want to thank my MSRP 2021 cohort. They're like family to me, and I'm super grateful to be able to have an awesome work and social environment created by them here at MIT. So thanks so much for coming to listen to my presentation, and have an awesome day.